There is a detail in the stone of the Great Pyramid that photographs never pick up. You have to be close enough to put a hand flat against a block. And the light has to be low, coming in sideways, throwing shadows across the surface. Then they show up. Small, pale discs packed tight into the limestone, most of them about the width of a fingernail, some as broad as a coin, a few of them broader than that. They are shells. Each one held a single living cell. One cell, which built itself a coiled chamber of calcium and settled on the floor of a warm, shallow sea. And there were numbers of them that nobody has ever managed to put a figure to. They lived and died and sank, and their shells piled up on the seabed across millions of years, and the weight of the water and the weight of everything above pressed that pile into rock. The rock is called Mokattam limestone, and it is what the pyramids are made of. The men who quarried it were cutting into a seafloor. The sea had been gone for roughly 40 million years before the first block was ever moved, and one of the largest things human beings have ever built is made, almost entirely, of some of the smallest things that ever lived. That sea has a name now. We call the stretch of time it belonged to the Eocene. It ran from about 56 million years ago to about 34 million years ago. 22 million years is a hard number to do anything useful with, so here is one to set beside it, our own genus, the branch that holds every human being who has ever lived, and several kinds of people who no longer exist, is a little under 3 million years old. The Eocene is roughly 8 of those, laid end to end. It was the last time this planet was warm all the way through. Not warm the way a good summer is warm, but warm as a setting, a condition the whole Earth was simply left in for millions of years at a stretch. At the height of it, the global average sat somewhere near 27 degrees Celsius, about 13 degrees above the average of the world we were born into, and the carbon dioxide in the air reached something like 1,600 parts per million. There was no permanent ice at either pole. That is an easy sentence to read past, so it is worth slowing down for. On the coast of what is now Antarctica, at a latitude where the ice today lies kilometers deep, there were forests. Not the low, hardy, cold-adapted kind. Forests carrying palms and relatives of the baobab in a place where winter temperatures stayed above 10 degrees and, as far as the record shows, never once produced a frost. At the opposite end of the world, on islands in the Canadian high Arctic that are polar desert today, there were alligators, giant tortoises, heavy, hippo-shaped plant-eaters moving through swamp forest. Hundreds of kilometers north of anywhere a reptile can survive now. And warmth changes the temperature. It does not change the light. Those islands sat at the same latitude then that they sit at now, which means the sun still went down in autumn and stayed down until spring. The same long dark you would meet there tonight if you went. Whatever else was different about that world, the alligators of the Arctic spent months of every year in total darkness. They just did it without the cold. It is tempting to file all of this under strangeness, a fever the planet ran and recovered from, before returning to something like its proper self. The record does not really support that reading. Across the long history of this Earth, conditions like the Eocene are closer to ordinary than to exceptional, and permanent ice at both poles, holding through every season of every year, is the unusual arrangement. It is also the only arrangement any of us has ever known, which is precisely why it feels like the floor under everything, and why the Eocene feels like a departure from it. We are the ones living in the strange chapter. If you could set yourself down anywhere in that world, almost nothing would look right. India was still closing on Asia, and the Himalayas had not been pushed up. The Atlantic was narrower. A shallow sea lay across the Middle East, where there is desert now, and that sea is where the pyramid stones were made. Out in the water off what would become Pakistan, whales were still learning how to be whales, and some of them still had legs. The first horses stood about the height of a house cat, and over the next 100,000 years they would get smaller before they got bigger. It is worth pausing on how any of this is known. We arrived long after the warmth had gone, into a cold and narrow slice of time, with no memory of it and nobody left to ask. And the Eocene was reconstructed anyway, out of shells and the shapes of leaves and the chemistry of very old mud, by people who spent whole working lives on a few meters of rock. None of us will ever see that world. It exists now only as a reconstruction, assembled slowly, argued over, taken apart and put back together, and as far as we can tell, it is true. Before we walk into it though, if you find yourself drawn to these slow descents into deep time, to the patient business of walking through worlds that are gone, consider subscribing to continue these journeys with us. There is a great deal of this planet's past still to cross, and it is better crossed unhurriedly. And let us know in the comments where you're listening from tonight, your city, your time zone. It's always something to see how far a quiet hour like this travels. All these different cities going dark at slightly different times, all of us awake in the same curiosity about a world that was warm long before it was ours. Now let's begin our journey. Not in the Eocene itself, not yet. We begin in a room in Paris in the early 1830s at a table covered in shells where two men are working their way through a collection and are about to give this epoch its name. Gerard Paul Deschamps picked up a shell the size of a thumbnail, turned it over once and set it down to his left. It was ridged along its length, chalky under the thumb, about the colour of weak tea. He had already worked through several thousand like it, and there were several thousand still to come. Deschamps was among the finest conchologists in Europe, a specialist in shells, which meant he had given his working life to distinctions almost nobody else could see. The number of turns in a spiral, the angle where the lip of an opening meets the body, the fine ribbing that separates one small buried animal from another small buried animal, both of them dead for millions of years, neither of them ever given a common name in any language. Most of the shells on the table were not his. They had been carried to Paris by a man named Charles Lyell, who was in the middle of writing a book about how the world got to be the way it is, and who had run into a problem that was, underneath everything, a problem of filing. Everyone in geology agreed that layers of rock stack up in order, and that lower means older. Nobody could say by how much. And the vast middle portion of that stack, everything between the age of the great reptiles and the world of the present, sat there as one undivided mass, too long to be useful and too poorly understood to be split. Lyell's answer was to count. Every one of those deposits held shells, and each shell belonged to a species that was either still alive somewhere in the world's oceans, or was not. Some of them a person could go and find on a coast that afternoon. Others were gone, everywhere, permanently. The balance between those two groups ought to shift in a regular way as you moved down through the stack, because species drop out of the world at a rough and steady rate, and the deeper you go, the fewer of the survivors should remain. The measure was extinction itself. The more of a deposit's animals had disappeared from the living world, the older the deposit had to be. Which is why the two of them were at a table in Paris, working through it a single shell at a time. Deschamps knew the living mollusks of Europe well enough to say, for almost anything set in front of him, whether the animal that built it was still out there. Lyell kept the tally. No instrument existed that could help with this, and no shortcut suggested itself. There was a shell and a judgment and a mark on paper, and then the next shell, and this went on for months. If you had walked into that room without knowing what you were looking at, you would have seen two men doing clerical work. What they were actually doing was building the first working measure of deep time out of seashells by hand. The figures came out cleanly enough to name things by. In the youngest deposits, a large share of the species were still living. In places, the majority of them. Further down, the share fell away, and in the oldest of the three groups, at the bottom of the stack, almost the whole assemblage had gone. Somewhere around 3 species in every 100 were still alive, and the other 97 had closed behind that world and stayed closed. Lyell built the names out of Greek. The middle group became the Miocene, meaning less recent. The youngest became the Pliocene, more recent. And the oldest, where the tray was almost entirely full of animals that no longer existed anywhere on Earth, he called the Eocene, from Eos, dawn, and Kainos, new. The dawn of the recent, first light of the world we are standing in. The third volume of Principles of Geology carried the division into print in 1833, and it held. It is worth being exact, though, about what was inside that book and what was not. Lyell could give you the order. The Eocene came before the Miocene. Both lay a long way beneath anything with a person in it. The sequence ran in one direction and never doubled back. What he could not supply was a date. In 1833, there was no method anywhere for putting a number of years onto a piece of rock. None existed, and none would exist for roughly another 70 years, until the discovery of radioactivity handed geologists a clock that runs on the decay of atoms. Had anyone asked him how old the Eocene was, the honest answer available to him was that it was very old, and older than the layer above it. 1 million years, or 300 million. He had no way to choose between them. When the real numbers finally arrived, they filled his framework in rather than replacing it. The order he had assembled out of shell counts turned out to be right. The lines have been redrawn since, more than once, and in places by a good margin. So the Eocene we mean tonight is not precisely the Eocene he meant, but the shape is his, and the name is his, and every date in this story hangs on a scaffold that 2 men built at a table with their hands. What we mean by it now is fixed at both ends by agreement, and both of those agreements are strange. The bottom of the Eocene sits in a hillside at Dababia in Egypt, a short distance from Luxor. It was ratified in 2003 after years of argument, and what it marks is neither a fossil nor a change in the kind of stone. It is a change in carbon. At one particular level in that hillside, the balance of carbon in the world shifts to a different mixture, a signature that shows up in ocean sediment everywhere on the planet at the same moment. That is where the epoch starts. Stand in front of the rock face, and what you will see is rock. The top of it is in a quarry at Massignano, on the Italian coast near Ancona, agreed in 1992. What marks that one is the disappearance of a single-celled organism called Huntcanina, a floating thing too small to make out without a microscope, which built itself a shell with long hollow spines running off it. Huntcanina drifted in the open ocean for millions of years, and then at one level in that quarry it simply stops appearing. Nothing above the line has ever been found. The epoch ends where a plankton runs out. So this stretch of time is bracketed underneath by a change in the chemistry of air and water, and on top by the last appearance of something invisible. Both boundaries are real, in the sense that they can be found, argued about, and driven to. Neither can be seen. You could stand at either one with a hand laid flat on the rock, covering the entire transition, and there would be nothing to look at. No line, no shift in colour, nothing that announces anything. There is a symmetry in that worth pausing on. The limestone the pyramids were cut from is packed solid with the shells of single-celled organisms, and the end of this same epoch is marked by another single-celled organism from the same broad family ceasing to be. creatures individually too small to see, present in numbers nobody has ever managed to count, hold both ends of this story, building the monument at one end and closing the door at the other. Both of those lines are decisions, careful ones, fought over for years by people who care about them a great deal, but decisions nonetheless, drawn by human beings into rock long after everything they describe had finished happening. What the lower line points at is not a decision. Something happened to the air of this planet around 56 million years ago. It came on slowly enough that nothing alive could have felt it inside a lifetime, and thoroughly enough that the mud on the floor of every ocean in the world wrote it down. Whatever it was, it came first, and the warmth that settled and held, the forests that ran all the way to the poles, and the ice that eventually arrived and never left all stand downstream of it. Somewhere in the middle of a core of pale grey mud drawn up from the floor of the Weddell Sea off the coast of Antarctica, there is a stretch where the small things stop. Above that stretch and below it, the sediment is crowded with the shells of single-celled organisms that lived down on the sea floor in the cold and the permanent dark. Through the stretch itself, a great many of them are gone. The bottom dwellers took a heavy loss. A large share of species that had been living quietly down there for millions of years do not appear again above that level, anywhere, in any core, on any ocean floor in the world. And there is nothing in the rock that explains it. No ash, no shattered quartz, no debris from anything falling out of the sky. None of the physical wreckage a catastrophe generally leaves lying about for somebody to find later. What there is instead is a change in the carbon. Carbon comes in slightly different weights, and living things prefer the lighter kind. Anything that was once alive, a forest, a peat bed, methane locked into frozen sediment, carries a carbon signature measurably lighter than the carbon of the ocean and the atmosphere taken as a whole. At the base of the Eocene, the carbon locked into shells everywhere on the planet swings toward the light, and it swings hard. Something released an enormous quantity of once-living carbon into the air and the water, in a quantity and at a pace that overwhelmed every process the Earth normally uses to keep that balance steady. Kennett and Stott published the Weddell Sea record in 1991, and what they laid out was three things arriving at the same level: an abrupt warming of the deep ocean, the shift in the carbon, and the die-off among the animals on the sea floor. The following year, working on hardened nodules of ancient soil from a basin in Wyoming, Koch, Zakos, and Gingerich found the identical carbon shift on dry land, on a different continent, in rock that had never been anywhere near the sea. That match is what settled the size of the thing. A signal in one ocean might be an ocean's private business. A change in currents, a local failure of circulation, something regional. The same signal in the soil of a continent thousands of kilometers away means the carbon was never in the water to begin with. It was in the air. All of it, everywhere, at once. The warming that came with it is easy to state badly, so it is worth going slowly. The late Paleocene world, immediately before any of this, was already hot. The global average sat somewhere around 26 degrees Celsius, about 12 degrees warmer than the modern average, with no permanent ice at either pole and forests running to high latitudes. That was the baseline. What the event did was take an already warm planet and push it several degrees further, to a peak somewhere near 32, 5 degrees, or 6, or as much as 8, depending on which records you weight. But 5 degrees added to a world that had no cold left in it to give up. Then there is the question of how long, and this is where the whole thing becomes something other than a disaster story. The event has a shape, and the shape is well resolved. The onset, the arrival of the carbon, the part anybody would point to as the event itself, took somewhere between 1 and 5,000 years, and the more careful reconstructions put the floor of that at 4,000. After that came the body of it, 70 to 100,000 years in which the world sat at its new temperature and did not come down. Then a recovery of another 50 to 100,000 as the system slowly worked the carbon back out of the air and locked it into stone. 200,000 years, give or take, from the first stirring to the last. What we still cannot say is what set it off. There is no shortage of candidates, and that is part of the difficulty. The North Atlantic was tearing open at exactly this time, and the volcanism that came with the tearing was on a scale that is hard to hold in the head. Magma forcing its way up through thick beds of organic sediment would have cooked methane out of them in enormous volume. There is methane frozen into the ocean floor, held in place by cold and pressure, which turns unstable when the water above it warms. There is permafrost. There are peat deposits that could have caught and burned. There are shallow seas that could have dried out and let everything organic in them oxidize into the air. Measurements of boron published in 2017, which track how acidic the ancient ocean was and therefore how much carbon it was taking up, pointed toward the volcanic source and toward a total larger than anyone had previously supposed. That reading has held up reasonably well. It has not closed the question. Some of the carbon still looks too light to have come from magma alone, which leaves the frozen methane in the story as a consequence rather than a cause. Warming that released more carbon, which drove more warming, in a loop that fed itself until it ran out of fuel. So the honest position is this: we can locate the beginning of the Eocene to within a few thousand years, chart its temperature, follow its recovery in detail, and drive to the hillside where the line is drawn. We do not know what started it. The word used for all of this in the papers and in the textbooks is abrupt, sometimes sudden. It is the correct technical term, and it means fast relative to everything else in the geological record, which is a fair description. Set a human number beside it, though, and something turns over. Everything our species has ever written down. Every clay tablet and scripture and law and letter, the entire documentary record of human beings from the first accounting marks scratched into wet clay to the words being spoken now, covers something in the region of 5,000 years. The onset of this event, the fast part, the part that arrived too quickly for the planet to absorb it, took at least 4,000. The event in full ran roughly 40 times longer than the whole of everything we have written, which means that nothing alive experienced it. That is the part worth staying with for a moment. In those 200,000 years, not one animal on Earth lived through a changing climate. Every one of them was born into a world, moved around in it, raised whatever it raised, and died. And the world on the day it died was the world on the day it was born. Generation after generation after generation, and none of them inherited anything but a slightly different normal. The event is only an event from up here, standing at the far end and looking down the length of it. From inside, it was weather. You can go and stand at it as it happens. The interval turns up in a good many places, but one of the most complete sights in the hillsides of a basin in northern Wyoming, where the whole thing is laid out in sequence. And you can walk up through 200,000 years on an ordinary afternoon, in the sagebrush, in the wind, with a road not far off. The rock itself does not look like much, which by now should not be surprising. But there are teeth in it, small ones, working loose from the slope, belonging to animals that fed and bred and died their way through the entire span without any of them suspecting there was anything to get through. And the teeth are not all the same size. Walk up that hill in the right order and they get smaller. At its smallest, the animal weighed a little under 4 kilograms. It stood about as tall as a house cat and weighed about what a house cat weighs. It had toes rather than hooves, several to each foot, spread slightly wide for soft ground under trees. Its teeth were low and rounded, built for leaves and shoots because there was almost no grass anywhere in the world yet for anything to eat. That came much later, and when it did, it rebuilt half the mammals on Earth. This animal browsed. It lived on a forest floor in what is now Wyoming, in heat, in heavy shade, and it belonged to the family that eventually produced the horse. The teeth come out of a hillside in the southern Bighorn Basin near the town of Worland. A team led by Secord published what was in them in 2012, and the method is worth slowing down for because it is unusually clean. Tooth-size scales with body size in mammals, closely enough that a measured tooth gives a fair estimate of the animal it came from. So the teeth record how big these horses were. But tooth enamel also takes up oxygen from the water the animal was drinking while that tooth was forming, and the different weights of oxygen in it carry a temperature signal. The same tooth is therefore both the measurement and the thermometer. Nobody has to line up two separate records and hope they agree. The size of the animal and the warmth of the world it was standing in come out of one object a few millimeters across, small enough to balance on your thumbnail. What came out was this. At the beginning of the event, the horses ran to about 5.5 kilograms. Across the following 130,000 years, as the temperature climbed, they became steadily smaller, around 30% smaller, until they bottomed out under 4. Then, over the last 45,000 years of the event, as the world let go of the heat, they grew again, past where they had started, to something close to 7 kilograms. Plot the body size against the temperature, and the two lines make nearly the same shape. The explanation most of the work points to is an old and fairly dependable observation about warm-blooded animals. Within a related group, the ones living in hotter places tend to run smaller. A large body holds heat well, which is worth having in the cold, and a burden in the heat, where the whole problem is shedding it. A small body carries more surface for its volume and cools faster. Over enough generations in a warming world, selection quietly favors the smaller ones, and the average slides down. The horses were not alone in it. Several other mammal groups in the same rocks shrink across the same interval, which suggests something general was pressing on all of them rather than something peculiar to one family. There is also a second possible factor that is less settled. Plants grown in air richer in carbon dioxide tend to come out less nutritious, more bulk and proportionally less protein, so a browsing animal gets less from every mouthful. Whether that was doing real work here has not been established. It is a reasonable suggestion that has not been pinned down, and it belongs in the account as a suggestion. Now, there is a thought that tends to arrive around here, and it arrives because most of us were taught to have it. The thought is that the little horse was on its way somewhere, that it was a first attempt, a horse in progress, undersized and confused about its toes, working toward the animal standing in a field down the road. In that reading, the shrinking is a wobble in an upward line, a bad decade in an otherwise promising career. That picture has a specific origin, and it helps to know where it came from. In the 1870s, the American paleontologist Othniel Marsh laid out a series of fossil horses in order, small to large, many toes to one hoof, low teeth to high. He had the material to do it because the horse family left one of the finest fossil records of any group of mammals, and most of it happened in North America. When Thomas Huxley came to look at the collection, he was convinced, and said so loudly and in public. The sequence went into museum cases and from there into textbooks, and it has been redrawn in essentially the same form ever since, 5 or 6 animals in a row, growing, losing toes, ending with a modern horse facing right. As a demonstration that living things change over time, it did honest work, and it persuaded a great many people who needed persuading. The difficulty is in what the arrangement implies. A row of animals in ascending order looks like a road with traffic on it moving one way. What the fossils describe is a bush. At almost every point in this family's history, there were several kinds of horse alive at the same time. Different sizes, different diets, different continents. Three-toed animals feeding alongside single-hoofed ones for millions of years. Nearly every one of those branches simply ends. The clean line running from the small forest browsers to the animal in the paddock exists because that particular twig is the one that happens to still be alive, and a line can be traced to any surviving twig on any bush provided everybody agrees beforehand to ignore the rest of it. The size story does not survive close reading either. Work by Bruce McFadden on body mass across the whole family found that for roughly the first half of the horse's history, tens of millions of years of it, size showed no consistent upward trend whatsoever. It drifted slowly, and it drifted both ways. The wide range of horse sizes, including the genuinely large ones, arrived a great deal later. As for the animal at the bottom of the diagram, the one that generations of schoolchildren learned as Eohippus, the dawn horse, specialists have since broken it apart into several separate genera, some of which may not sit on the horse line at all, and the name has largely fallen out of professional use. Take the road away, and the little horse looks different. It was a finished animal, well matched to a hot forest floor, doing the only thing any lineage has ever done, which is to fit whatever is in front of it. Nothing about it was early, and nothing about it was headed anywhere. The world warmed, and its descendants got smaller, because smaller worked better in the heat. The world cooled, and they got larger again. There is no ambition in that, and no direction to it. There is an animal, and a temperature, and a very great deal of time. There is also more room to breathe in it than the ladder ever offered. A creature you could have lifted with one hand, in the shade, in the heat, growing gradually slighter across 130,000 years and gradually heavier across the 45,000 that followed, not climbing toward anything, not behind schedule, not a draft of something better, answering the weather, which is all any of them were doing. The heat moved more than horses, though. Something else turns up in those same Wyoming rocks at the same level, and it turns up abruptly, as if a door had been left open. Whole groups of mammals appear that had never been on the continent before. The even-toed animals, whose descendants include deer and cattle, and, stranger than it sounds, whales. The odd-toed ones, of which the little horse was a member. And a small, sharp-faced, forward-eyed thing living up in the branches, belonging to the order that eventually produced us. None of them evolved there. Every one of them walked in, and the distances they covered, measured against the time they had to cover them, are difficult to credit even now. How do you tell which direction an animal was walking 56 million years after it stopped? The animals in question are very small. Most of what survives of them is teeth, a few jaw fragments, the occasional crushed and flattened skull, nothing you would notice in a quarry unless you were looking for it with a hand lens. They lived up in the branches. They had forward-facing eyes set close together, hands that closed around things, and nails where their ancestors had carried claws, which taken together is the anatomical signature of the order we ourselves belong to. And within a very short interval, they appear in China, in Belgium, and in Wyoming. Not close relatives on 3 continents. The same genus, a little tree-dwelling insect-eater called Tailhardina, small enough to sit in a cupped palm, turning up in rocks on both sides of the world, at what looks, from a distance, like the same moment. They are part of a larger arrival. At the base of the Eocene, 3 groups of mammals appear across the whole northern hemisphere with no local ancestors underneath them. Nothing in the older rocks of North America or Europe that could plausibly have produced them. The even-toed animals arrive, the ones that would eventually become deer and pigs and camels. The odd-toed ones arrive, including the little horse in the Wyoming hillside. and the true primates arrive, forward-eyed and grasping, and go up into the trees. 3 of the orders that still run the terrestrial world today walk onto 2 continents inside the space of a heat wave. So the question of direction is not academic. Somewhere on Earth, those animals already existed, and everywhere else they had to come from there. The answer runs on 2 things, and the first of them is the carbon. That swing in the carbon at the base of the Eocene, the one that shows up in ocean mud and in ancient soil alike, is not only a boundary, it is a clock, because the shift happened everywhere at once and left the same signature in every kind of sediment. It can be picked up in a marine core off Antarctica, and in a riverbank deposit in Belgium, and in a hillside in Wyoming, and used to line those places up against each other. And the shift is not a single event, but a shape, with a rapid fall, a long flat body, and a slow recovery. So a fossil can be placed not merely inside the event, but at a particular point along it. It becomes possible to say that this jaw from China sits low in the excursion, and that jaw from Wyoming sits somewhat higher, and to mean something quite precise by it. Without that, none of this would be answerable. A migration across 3 continents in a geological instant would look in the rocks exactly like 3 unrelated populations appearing independently. The second thing is anatomy. Populations accumulate small changes as they spread, and the forms carrying more of the ancestral features tend to sit nearer the origin, while the ones further along have drifted further from it. Put the 2 together and a root falls out. Smith, Rose and Gingerich published it in 2006. The Chinese material is oldest, the Belgian material is younger, and the 2 North American forms are younger still. The genus moves west, out of Asia, across into Europe, and then on into North America, and the whole passage, from the earliest specimen to the latest, occupies something on the order of 25,000 years. That figure deserves a note of caution, and the note is worth making because it is the same difficulty in a different form. When the entire event you are measuring lasts 25,000 years, and your dating resolution is itself in the thousands, the ordering of the very oldest specimens sits close to the edge of what the method can resolve. The sequence has been revisited more than once since, and the fine details of who arrived where first are still argued over by people who know the material intimately. What has held is the shape of it, an Asian origin, a westward spread, and a speed that nobody expected. The road they took existed only because of the heat. Between Europe and Asia at that time lay the Turgai Strait, a long shallow seaway running roughly north to south, which for most of the preceding age had kept the 2 landmasses apart as effectively as an ocean. And between Europe and North America there was no Atlantic worth the name. The 2 continents were still joined, or nearly joined, across the far north, through Greenland, which today would be a sentence about ice. It was not a sentence about ice then. The high Arctic in the early Eocene was forested, wet and warm, and the connection through Greenland was not a frozen bridge to be endured, but simply more forest, continuous with the forest on either side of it. An animal moving through it would not have known it was crossing anything. It would, however, have been walking in the dark for part of every year. That country sat at very high latitude, and latitude is one of the few things the warmth could not touch. Whatever the temperature was doing, the sun still left for months at a time. Our own order arrived on this continent through a warm forest at the top of the world, in a winter darkness that no primate alive today would tolerate for a week. And here is where the picture quietly rearranges itself, because none of these animals were going anywhere. No individual crossed anything. A small tree dweller with a life of a few years does not conduct an intercontinental migration. It is born in a patch of forest, feeds in it, breeds in it, and dies within a short walk of where it started. What was moving was the forest. As the world warmed, the belt of country warm enough and wet enough to support that kind of woodland expanded north and expanded west, into ground that had been closed to it, and the animals living inside that belt did the only thing available to them, which was to stay inside it. Each generation occupied the edge its parents had reached, and the edge kept advancing, and after enough generations the population had crossed a world without a single one of them taking a journey. 25,000 years is roughly 1,000 human generations, 1,000 grandmothers laid end to end, from a woman alive today back to one who lived when the ice was still thick over northern Europe. That is the span the crossing took, and against the 200,000 years of the event that permitted it, 25,000 is a fraction. One small movement inside a longer one, over almost before the warmth had finished arriving. There is something worth holding in that, in a quiet way. Everything about the order we belong to on this continent, every lemur that ever lived here, every monkey, and eventually every one of us, traces back to a small forward-eyed animal that entered through the Arctic, in the dark, in the heat, without deciding anything, because the trees it needed had spread far enough north for it to follow. The heat that opened those roads did not last. The carbon worked its way back into stone, the temperature came down, and the world returned to something closer to what it had been before, the way a system does when the thing pushing it lets go. But it did not stay down. Over the following 2 or 3 million years, the temperature began to climb again, without any spike this time, without any sudden delivery of carbon. A slow, general, unhurried warming that arrived and then simply stayed. What came out of that rise was not an event at all. It was a condition, and the world settled into it for 4 million years. A leaf lies flat on a piece of split shale, and it is a good deal larger than the leaves outside the window. Its margin is smooth, no teeth along the edge, no serrations, just an unbroken line running from the stem out to the tip. And the tip is drawn into a long, narrow point, the shape botanists call a drip tip, which exists to shed water quickly enough that the leaf never stays wet long enough to rot. Both of those things are climate. Trees in cool places tend towards smaller leaves with toothed edges. Trees in warm, wet places tend toward large ones with smooth margins, and where the rain is heavy and frequent, they grow the drawn-out tip that lets it run off. No single leaf proves anything. Gather a few hundred from the same bed, count the proportions, and you have a thermometer and a rain gauge in the same handful of stone. The forest that leaf fell out of was closed over, canopy against canopy, the floor of it in permanent green shade. Rain came heavily and often. Fallen wood did not last. Rot in that heat worked quickly, and almost everything that reached the ground was taken apart and folded back into the soil within a few seasons. Standing under it at midday, you would have found the light thin and the air thick, with water moving somewhere below the leaf litter whether or not it had rained that morning. What you would not have found anywhere is open ground. There were no grasslands. Grass existed in modest quantities in a few damp corners of the world, but the great open systems, prairie and steppe and savanna, the entire category of country where the ground is covered and the sky is not, had not yet been invented and would not exist for tens of millions of years. Every part of the land surface that could support trees was supporting them. A traveller could have walked from one end of a continent to the other and never once come out from under a canopy. The shape of the world helped. India was still an island making its way north and had not yet arrived. Australia was still fastened to Antarctica, or only beginning to come away from it. And running east to west across the middle of everything was the Tethys, a wide, warm sea, open at both ends, joining what is now the Atlantic to what is now the Indian Ocean through the ground that would later be crumpled up into the Middle East. Warm water could travel most of the way around the planet without ever leaving the tropics. It did, and it carried the heat with it, and the difference in temperature between the equator and the far north was far shallower than anything we have ever measured. This interval has a name, and the name is worth stopping over because it misleads in a way that is nobody's fault. It is called the early Eocene climatic optimum. Roughly 53 to 49 million years ago, the warmest sustained stretch of the last 66 million years, with carbon dioxide reaching something near 1600 parts per million around 51 million years ago, the highest reading anywhere in that whole span, and a global average close to 27 degrees Celsius. Optimum in that phrase does not mean best. It is technical usage inherited from a period when warm intervals were routinely described as favorable, and what it denotes is a maximum, the top of a curve, and nothing more than that. The word carries its ordinary meaning along anyway, though, and it is fair to ask what should be made of it. The honest answer has no single edge. Measured by the sheer quantity of living tissue on the planet and by how much of the Earth's surface was hospitable to something, this was an extraordinarily productive world. Forest standing where there is now permanent ice, diversity climbing in most of the groups we can count. Measured another way, by whether the tropics were comfortable, by what became of organisms already sitting near the limits of what they could tolerate, the picture is less generous, and a fair amount of it remains unclear. Good for life turns out not to be a question with an answer. It is only ever a question about which life. The word means maximum. It is probably best to let it mean only that. Work published in 2020 gathered the whole of the last 66 million years into one continuous record and found that the Earth has not drifted evenly across that time. It has instead occupied 4 fairly distinct settings: a hot one, a warm one, a cool one, and a cold one, with transitions between them. On that reading, the early Eocene sits in the hottest of the 4, and everything since has been a long descent through the other 3. We are at the bottom of it, looking up. What is hardest to convey about any of this is not the heat. It is how long it went on. The plateau ran for something in the region of 4 million years. Not 4 million years of change, 4 million years of the same thing. The temperature moved, the way temperature always moves, but it moved around a level and kept coming back to it, the way a heated room holds its warmth while the air inside it turns over. Set that earlier carbon event beside it for a moment. 200,000 years beginning to end. Long enough to shrink the horses by a third and grow them back. Long enough to open a road through the Arctic and let 3 orders of mammals walk into 2 continents. That entire event fits inside this plateau 20 times over. 20 of them laid end to end, and you would still only have crossed the warm part of the early Eocene. Nothing about it was dramatic from inside. A small animal in that forest lived and died in a climate identical to the one its parents had known, and its grandparents, and every ancestor stretching back further than any lineage keeps account of. And it would be the same for every descendant for as long as the line ran. Something like 2 million generations of tree-dwelling creatures for whom the world was simply this, and had always been this, and gave no sign of intending to be anything else. 4 million years of a planet that asked nothing of anyone, not recovering from something, not building towards something, warm and wet and covered over, and entirely uninterested in being noticed. It registers with us at all only because we turned up a very long time afterward and went looking through the mud. And in one corner of it, far to the north, on an island that no human being would stand on for another 45 million years, tall trees were growing on wet ground near a river. They were ordinary enough for their time and place. Some of them lived for centuries. They dropped their needles every autumn, which is an odd thing for a conifer to do, and a clue in its own right. One of them came down. Water and fine silt closed over the stump before rot could reach it, and sealed it, and kept it, and it is still there, and it is still wood. Nothing grows on the eastern side of Axel Heiberg Island. It lies at close to 80 degrees north, well inside the Canadian Arctic archipelago, and the ground there is loose grey gravel and frost-shattered stone, cut through in summer by meltwater channels and silent for the rest of the year. There is no soil to speak of. There are no trees within 1,000 kilometers. Two people working a geological survey field season came over a rise in 1985 and found themselves looking at tree stumps. Not impressions of stumps left in stone, and not mineral casts of them either. Actual stumps rooted where they had grown, standing in the positions they had held while they were alive and spaced out across what had plainly been a forest floor. Between them lay the forest's own litter, mats of fallen leaves, cones, scattered needles, the accumulated drop of one season after another lying more or less where it had come to rest. Nothing about the arrangement had to be reconstructed. The arrangement was simply still there, on the ground, under a sky that has not grown a tree in tens of millions of years. And the material itself behaves like material rather than like rock. Pick up a piece, and the first thing that registers is how light it is. It is dry in the hand, and brown, not the grey or the rust of mineralized wood, but an ordinary wood brown, the colour of something that has spent a long time in a shed. Draw a thumbnail across the surface, and it catches on the grain. Work at it, and it splits along that grain the way an old fence post splits, with the same fibrous reluctance and then the same clean parting once it finally goes. Small fragments can be lifted straight out of the ground with tweezers and will not crumble on the way up. Museum collections holding pieces of it report that a fragment will still take a flame. This is the part worth stopping on, because the temperature is a distraction. Trees at 80 degrees north makes a striking sentence, and it does the work that striking sentences do, but warmth at high latitude is on its own explicable. Carbon dioxide was high. The temperature difference between the equator and the far north was shallow. A world like that can be produced without anybody straining. What is genuinely hard to take in is the wood. When something organic becomes a fossil in the ordinary way, it is replaced. Groundwater carrying dissolved minerals works through the tissue and swaps the original material out for stone, cell by cell, until nothing of the first substance is left. Petrified wood is an exact copy of a tree rendered in silica, faithful down to the cell walls, and there is no wood in it anywhere. The tree is gone. What remains is an extremely good description of the tree, written in mineral. None of that happened here. The trunks went into wet, fine-grained sediment quickly enough, and into ground poor enough in oxygen, that the fungi and bacteria which take wood apart never properly got going. And then, for 45 million years, nothing else happened to them either. No mineral flooding, no serious heat, no pressure worth the name. The original organic material simply stayed where it was and waited. Those stumps are not a record of a forest, they are the forest. Set the number against anything else made of wood and it stops behaving like a number. The oldest wooden buildings still standing anywhere on Earth are a little over 1,300 years old, kept upright on purpose by many generations of people who cared about keeping them upright, repaired and re-roofed and watched. That is roughly the outer limit of what sustained human attention has managed to preserve in timber. The wood on that island is something like 35,000 times older. Nobody looked after it. It was buried in mud, forgotten by the entire living world, and came through anyway. What grew there was mostly dawn redwood, a tall, straight, fast-growing conifer with soft, flat needles. It is not an extinct tree. Stands of it are still alive in central China, and you can walk under one on an ordinary afternoon and put a hand on the same kind of bark. Around it in the Arctic forest grew larch and spruce, with birch and alder in the wetter ground, and the occasional broadleaf that would look unremarkable in a modern temperate wood. Some of those trunks, judged by their diameter and by how far apart they stood, carried crowns 30 meters up. Their growth rings can be counted because the growth rings are still there, real annual rings in real wood, and the older stumps run to several hundred, which means individual trees stood on that ground for centuries at a stretch, growing steadily, dropping their seasons onto the floor around them. The average temperature across the year worked out somewhere between 13 and 15 degrees Celsius, which is not tropical, and it is worth being clear that it was not. This was a mild, wet, temperate forest, closer to a coastal strip in the Pacific Northwest than to anything with palms in it. Warm, unhurried, rainy, and entirely ordinary except for where it was standing. There is one detail that refuses to sit comfortably with a temperate forest, though, and it is the needles. Dawn redwood is deciduous. It sheds every needle in autumn and stands bare all winter, which almost no conifer does, and which is expensive. A tree that empties itself out each year has to build an entire canopy again from nothing every spring. Evergreens exist precisely to avoid that bill. The island has not moved. It sat then within a few degrees of where it sits now, which means that for something like 4 months of every year, the sun did not come up at all, and for weeks on either side of that, it barely cleared the horizon before going back down. A tree carrying a full canopy through that darkness would be maintaining equipment it had no way to use. So it let the canopy go, stood there stripped and warm in the black, and waited for February. For a third of every year, that forest was mild, wet, and completely without light. The trees at least had the option of shutting down. Everything else living in there had to find some other way through. Warmth is a temperature. Darkness is a fact about geometry, and no quantity of carbon dioxide has ever done anything about it. The Earth is tilted a little over 23 degrees away from the plane of its orbit. It was tilted then too, by very nearly the same amount, and that tilt is the entire reason the far north spends part of every year turned away from the sun. Nothing in the composition of the atmosphere touches it. Heat the poles to whatever figure you like, and the sun will still go down in October and stay down until February. So put yourself in that northern forest at what ought to be the middle of the day, sometime in December, 50-odd million years ago. It is not especially cold, somewhere between freezing and 4 degrees, damp, with very little wind under the trees. The redwoods overhead have dropped their needles and are standing bare, and it is dark. Not dusk, not overcast gloom, but the full dark where the only light on the forest floor is whatever the moon and the stars are handing out, and it has been that way for weeks, and will be for weeks yet. For everything alive in there, this is the organizing problem of the year, and it is a food problem before it is ever a temperature problem. Photosynthesis stops, nothing grows, no new leaves, no shoots, no fruit, nothing green anywhere on the ground or above it for a third of the year. And there is no walking out of it. An animal would have to cover thousands of kilometers southward to reach daylight, and nothing in that fauna shows the least sign of having tried. What was living there is the part that takes some absorbing. Alligators. Small ones, close relatives of the animals in the southeastern United States today, in a forest at nearly 78 degrees north. Giant tortoises, too large to have dug themselves in anywhere. Snakes and lizards, fish in the channels. A tapir, big rhino-shaped browsers moving through the understory. A heavy, low-slung, hippo-shaped plant-eater called Coryphodon, which was the largest thing in the assemblage, and recovered from the same rocks and described only in the last few years. Primates, small, forward-eyed tree-dwellers, cousins of the animals that had come through this very country on their way into the continent a few million years before. The reptiles turn out to be the easiest to account for, and the logic runs backwards from what you would expect. A crocodilian does not need much. It is not paying to heat itself. Its body sits at whatever temperature the world is sitting at, and when the world cools, its metabolism drops with it, and its food requirement more or less collapses. A cool, wet, dark winter is no ordeal for an animal built that way. It is a long, cheap pause. Alligators at the northern edge of their range do a version of the same thing now, going close to inert through the cold months and living off what the summer put on them. What a crocodilian cannot survive is freezing. Ice ruptures tissue and slowing down offers no protection against it whatsoever, which makes those animals an instrument rather than a curiosity. What their presence establishes is narrow and quite precise. Hard freezing was rare in that forest. That is the claim the alligators support, and it is a smaller and more useful claim than warmth. The large plant eater is the harder problem because a big mammal has no such option. It has to stay warm through the dark, all of it, which means it has to keep eating. Its teeth say what it was eating. Through the light months, the chemistry locked into the enamel points toward fresh growth, leaves, new shoots, the ordinary intake of a browsing animal in a season when there is browse to be had. Through the rest of the year it shifts, and it shifts toward dead material, leaf litter off the forest floor, fungi, twigs and the softer tissue of wood, whatever evergreen needles were still hanging. An animal weighing several hundred kilograms, moving between bare trunks in the dark, working through last summer's fallen leaves. The temperatures themselves come out of oxygen locked into the animal's own bones and teeth. Eberle and colleagues put the warmest month at around 19 or 20 degrees Celsius, an agreeable northern summer by any standard, and the coldest month somewhere between 0 and 3.5, cool, damp, and just far enough above freezing that ice was not a regular event. The southern end of the world was doing something else entirely. Off the Wilkes Land coast of Antarctica, at roughly 70 degrees south, sediment lifted from the seafloor carries pollen from a lowland forest with palms in it and relatives of the baobab, and the reconstructed winter temperatures there sit above 10 degrees, essentially free of frost, in a place with the same polar darkness and rather less summer light. The two ends of the planet were not mirror images of each other. The southern one, at a comparable distance from its own pole, ran markedly milder through the dark months than the northern one did. And it is here that the evidence starts arguing with itself, which is worth watching rather than smoothing over. Palms have a limit. As a family, they cannot take sustained cold, and their presence in a fossil flora is normally read as requiring a coldest month above about 5 degrees. A few hardy lineages manage 2, but 5 is the working number. Palm pollen has been recovered from sediment cores taken in the Arctic Ocean, and palm remains have been reported from subarctic Canada. Both of those would place northern winters above that line. The animals from Ellesmere say 0 to 3.5. Both are careful measurements made by careful people. They are measurements of different things, at somewhat different places and somewhat different moments, and each carries its own load of assumptions. Pollen travels on the wind and out of rivers, and temperature read from isotopes depends on estimates of what the water was doing before the animal drank it. There is room in that for both to be correct about their own site and still disagree about the Arctic in general. There is also room for one of them to be wrong. The models come up against the same wall from the opposite side. A coordinated comparison of 8 climate models published in 2021 fed all of them the same early Eocene starting conditions and let them run. The old complaint about this period, that simulations could not warm the poles without overcooking the tropics, has largely been dealt with. The shallow temperature gradient comes out of processes that are well understood. The way air cools with height, the behavior of clouds, the heat capacity of a planet carrying no ice sheets, the effect of forest standing where there is now bare rock. What the models still cannot manage is the winters. Run them and high-latitude land comes out with a sharper seasonal swing than the fossils permit. Hotter in the summer, colder through the dark. Adjust the clouds to correct the gradient, and the seasonality gets worse rather than better. So, a set of computer simulations and a handful of fossil teeth approaching from opposite ends of the discipline have arrived at exactly the same question. It is no longer how the poles manage to be warm. That is more or less accounted for. It is how their winters manage to be mild. That is a good question to be stuck on, as questions go. It means the answer is already sitting in the mud somewhere, or in a line of code, and that somebody will find it eventually, and that it will very likely turn out to be something unremarkable that nobody had weighted properly. Meanwhile, the picture holds steady. A bare, mild forest at the top of the world, 4 months without a sunrise. Alligators lying dormant in the channels with their metabolisms nearly switched off. A large animal picking through the previous summer's litter in weather that never quite hardened into ice. A lineage will tolerate a great deal to stay where it is. A third of every year without light, a winter spent eating dead leaves, months of moving as little as possible, all of it evidently cheaper than leaving. But some lineages do leave, and while the Arctic was working out how to sit through the dark, on the shore of a warm, shallow sea most of a world away, a 4-legged land animal was spending more and more of its time in water it had no way to breathe. Wolf-sized, long in the leg, narrow through the skull, with a mouthful of teeth built for gripping something slippery, the animal standing in the stream shallows would not have struck anyone as the beginning of anything. The stream ran off high ground in what is now northern Pakistan and emptied into the northern margin of the Tethys, that warm sea running east to west across the middle of the world. 53 million years ago, this was river country, braided channels, silt banks, floodplain forest, the water warm and shallow and full of fish. The animal spent a good deal of its time in it, not swimming particularly, standing mostly the way a heron stands, with its feet on the bottom and its head down. It is called Pachycetus, and the first pieces of it came out of those hills in 1978, collected by Philip Gingerich, who was in the region looking for something else. It was named in 1981. For a long while afterward, it was reconstructed as a sleek, seal-like thing, because that is what the expectation demanded. More complete skeletons found later showed a running animal with long, slender limbs that waded and hunted and went home to dry land. It is a whale, not a whale-like animal, not an ancestor of something. By the definition working paleontologists actually use, it sits inside the group. Which raises the practical question, and the practical question is the interesting one. A 4-legged land mammal that wants to live in water has a list of problems to solve, and none of them are optional. It has to move, it has to hear, it has to drink, it has to manage its own buoyancy and breathe at an interface it cannot see through and give birth somewhere. The record in those Pakistani hills is a record of that list being worked through slowly, in no particular order, by animals that had no idea there was a list. Start with the moving, because it gives the whole thing away. A fish drives itself forward by moving its tail from side to side. A whale moves its tail up and down. That difference is not a stylistic quirk, and it is the single most legible piece of evidence anywhere in the animal's body that whales began on land, because up and down is how a running mammal already moves. Watch a dog at full stretch, or a rabbit or a cheetah. The spine flexes vertically, the back arches and extends, the hind legs swing forward underneath the body and then drive out behind it, and the whole animal works like a bow being drawn and released over and over in the vertical plane. Reptiles and fish bend side to side, mammals bend up and down. It is one of the oldest differences in the vertebrate body, and it has been sitting in our backs since long before there were mammals worth the name. Put a running mammal in water and the stroke it needs is already there. It does not have to invent a new way to move, it only has to make an existing motion more efficient, broaden the surface at the back end, thicken the muscle along the spine, reduce the drag at the front, and every one of those is a small change that a body can make in small increments without ever passing through a stage that does not work. That is what the rock shows. By around 48 million years ago, there is Ambulocetus, reported by Hans Tervissen in late 1994, whose name means walking whale and whose proportions are frankly crocodilian. Short, heavy limbs, very large feet, a long body, a build for lying still in an estuary and lunging. A couple of million years later comes Rodhocetus, described by Gingerich earlier that same year, and the vertebrae toward the rear of it carry enlarged attachment surfaces for muscle. The power is leaving the legs, it is going into the tail. The rest of the list gets worked through alongside it. The limb bones of these early animals are strikingly dense and heavy, far beyond what a runner needs, which is a wading solution, ballast, to hold an animal down on the bottom of a shallow channel instead of letting it bob about on the surface where nothing useful is happening. The opening for the nostrils begins creeping backward along the top of the skull, a few millimeters at a time across millions of years, moving toward the position where an animal can take a breath by breaking the surface with the top of its head rather than lifting its whole face out. And the oxygen locked into their tooth enamel shifts across the sequence. The earliest of them were drinking fresh water, off the land, out of rivers, and the later ones were not. None of it looked like anything at the time. Stand at the edge of that channel on some ordinary afternoon, and what you would see is an animal wading. It goes in, catches something, comes out, shakes itself off, lies down in the sun with its feet in the mud. There is nothing in the scene with any direction to it. It is not attempting the ocean. It is a competent predator working a productive edge, doing more or less what its parents did, in a place where the food happens to be underwater. The best way to hold what was actually happening is to borrow something nobody thinks of as change at all. 1,000 years ago, people in England spoke a language that a modern English speaker cannot read a line of without being taught it first. Nobody decided that. No generation ever woke up and agreed to move their vowels. Every person in that entire run spoke near enough the way their parents spoke, with small differences, mostly unnoticed, almost none of them deliberate. 40 generations of very nearly the same thing, and at the end of it, the language had become unrecognizable, and not one of those people ever experienced their language changing. Now run that same process at that same imperceptible rate for 8 million years. 8 million years is roughly twice as long as our own lineage has been walking upright. Every step of that, from the first apes that stood and stayed standing, through every species and subspecies and dead end, to whoever is listening to this now, would fit inside the whale transition twice over, with room left at both ends. And nothing in it was aimed at anything. The animals in the shallows were not on their way to the sea. Each of them was simply a little better suited to the shallows than its neighbors, in ways too small to notice inside a lifetime, and the shallows were where the food was, and the offspring of the better suited ones were a little better suited still. 8 million years of that, compounding quietly, and the shoreline had let go of them altogether. There is one item on the list that this has been walking around, and it is the ear. Hearing is the hardest of the problems. Air and water carry sound so differently that an ear built for one is close to useless in the other. And a mammal that lives underwater needs some way to get vibration into its inner ear through solid bone rather than through an air-filled canal. The solution these animals arrived at is a particular thickening of one particular bone in the skull, and it is unlike anything in any other mammal. Every whale alive has it. Every whale that has ever lived has it. Nothing else does. which mattered eventually for reasons that had nothing to do with whales at all, because that same bone, in a shape nobody was looking for, was sitting inside a block of stone collected in Kashmir in 1971, and for 36 years nobody opened it. It was about 70 centimeters long, built like a small deer, slender legs, a long tail, hooves on the ends of its toes, and it lived in what is now Kashmir around 47 million years ago. Nothing about it suggests the sea. It browsed on land. But the chemistry locked into its teeth says it spent a great deal of time in water, and the bones of its legs are dense and heavy in a way that a running animal has no use for and a wading animal does. It seems to have fed on the bank and gone into the streams to hide, standing on the bottom with its weight holding it there, waiting for whatever was hunting it to lose interest. In 1971, an Indian geologist named A. Ranga Rao was working those Himalayan foothills and came away with a quantity of stone. Out of part of it, he extracted a few teeth and a piece of jaw, enough to describe a small extinct hoofed animal and give it a name. The rest of what he carried out went into storage unopened. There is nothing unusual in that. Field collecting always outruns laboratory preparation, by years and sometimes by decades. A good season in good country produces more rock than a technician can work through in a very long time, and every serious collection in the world has shelves of material nobody has yet had the hours to open. The blocks are not forgotten. They are queued. Ranga Rao died in 1999 unexpectedly. His widow, Dr. Friedlinde Obergfell, took charge of the collection and kept it together, and some years afterward she passed the unopened Kashmir rock to Hans Tervissen, who had spent his working life on the early whales of Pakistan and India and would know what he was looking at. His technician was preparing one of those blocks when a skull broke. A vertebrate skull in hard matrix is a difficult object to get out. The bone is frequently no thicker and no stronger than the stone around it. And preparation means removing rock from bone with fine tools under magnification, hour on hour, with the constant live possibility of going a fraction too far. Skulls break. It happens in every preparation lab that has ever existed, and it is ordinarily a small disaster. This one broke across the ear, and the break exposed the inside. In most mammals, the bone that holds the eardrum is a thin ring or a thin shell, light, unremarkable, the sort of structure nobody would think to look at twice. In whales, one wall of that bone is swollen into a dense, involuted mass, and it exists because sound arriving through water has to be routed into the inner ear through solid bone rather than down an air-filled canal. It is called the involucrum. Every living whale and dolphin and porpoise has one. Every fossil whale ever recovered has one, including the long-legged waders standing in the Pakistani river channels. Nothing else does. Not one other mammal, living or extinct, anywhere. It was sitting in the ear of a small deer-like animal from Kashmir. The rock had come out of that hillside in 1971. The paper describing what was inside it appeared in Nature on the 20th of December, 2007. Some 36 years later, on top of the 47 million the stone had already spent waiting. And the thing that finally opened it was somebody's hand slipping. What that ear settled had been open for the better part of a century. The question was where whales came from, and the long-standing answer was a group called mesonychids, extinct hoofed carnivores, wolfish in build, carrying hooves where a predator would normally carry claws. Their teeth are triangular and serrated in a way that looks strikingly like the teeth of early whales, and for decades that resemblance carried the field. It went into the textbooks and stayed there. Anybody who learned this material before roughly the turn of the century learned mesonychids. The molecules disagreed. From the early 1990s onward, as it became possible to compare the genomes of living mammals directly, the result kept arriving and kept being unwelcome. Whales do not sit outside the even-toed, hoofed animals. They sit inside them, and the living creature they sit nearest to is the hippopotamus. Specialists in anatomy resisted that for years, and not unreasonably. The fossils said one thing and the genes said another, and fossils are the direct evidence. Then the fossils came around. Ankle bones from the early whales, once complete ones were finally in hand, turned out to carry a shape that occurs in even-toed animals and nowhere else. And the little wader from Kashmir turned out to belong to a small family of even-toed animals from India and Pakistan that sits closer to the whales than anything else so far found. The mesonychid teeth were a resemblance and nothing more. Similar shape, similar work, unrelated animals. By around 40 million years ago, the transition had finished, and what it produced is lying out in a desert in Egypt. Wadi al-Hitan, the Valley of the Whales, sits in the western desert southwest of Cairo, wind-cut sandstone with almost nothing living on it, and it holds hundreds of skeletons of fully marine whales from between about 40 and 37 million years ago. The sea they swam in was the Tethys. The desert is its floor, lifted up and dried out. The largest of them is Basilosaurus, which is an odd animal by any measure. 16 meters or more, extremely long and extremely narrow, built more like a serpent than like anything now alive. Beside it swam Dorudon, around 5 meters, compact, much closer to a shape anyone would recognize as a whale. In 1990, Philip Gingerich published a description of the hind limbs of Basilosaurus, recovered complete. Thigh bone, kneecap, shin, ankle, toes, the whole apparatus, properly articulated, with joints that worked. The entire leg is about 35 centimeters long. On an animal 16 meters from nose to tail, scaled to a person, that is a leg roughly the length of a thumb. It could not walk on it. Nothing about that limb could have carried the animal's weight or added anything to its swimming, and the most common suggestion for what it was doing, offered honestly and still a suggestion, is that it played some part in mating, as a guide or a grip. What is not in doubt is that it was there, fully made, on a creature whose ancestors had left the shoreline millions of years earlier and which had never in its life touched ground. Nothing about it is a stump or a vestige worn down to a nub. It is a leg with a knee in it, on a body the length of a bus. And the bone that settled the whole argument is one you are carrying. It sits deep in the side of the skull, a thin ring holding the eardrum in place, moving airborne sound toward the inner ear. The ordinary job it has performed in land mammals for something like 150 million years. In a whale, one wall of that same bone is grown thick and dense and heavy, because sound coming through water has to be handled another way. The same bone in the same position, solving a different problem. The ear is what settles it. Bodies change slowly and misleadingly. The legs hung on long after they had stopped mattering to anything. The ear went early and it went decisively, and it is still the piece of evidence that ends the argument. On the other side of the world, within the same handful of million years, something else was going down into the mud of a warm lake with its ears intact. It weighed about as much as a small apple. It had already worked out how to fly. And what is still argued over, seriously and without resolution, is whether it could yet hear the shape of the room it was flying through. Which came first, the flying or the hearing? Bats do two things no other mammal does. They fly under their own power, on a wing built out of a hand, and most of them navigate by shouting, producing sound, catching what comes back, and assembling from those returns a picture of the surrounding space detailed enough to take a moth out of the air in complete darkness at speed. Two remarkable capabilities in one small animal, and the obvious question about them is the order they arrived in. The best evidence sits in a lake in Wyoming, the same basin country, a few million years later, and a few hundred kilometers west of the hillside with the small horses in it. The lake is worth understanding before the bat is, because it is one of the finest recording instruments this planet has ever assembled by accident. Around 52 million years ago, there was a body of water in the southwest of that state, which geologists call Fossil Lake. It was the smallest of 3 lakes that occupied the region across several million years, and it was not deep in any dramatic way. What made it extraordinary was the condition of its floor. The water did not turn over. Warm surface water sat on top of cold, still, oxygen-free water beneath, and nothing disturbed that arrangement for very long stretches. The bottom of that lake was, in biological terms, dead. No worms, no burrowing larvae, no scavengers, nothing living down there to take apart whatever arrived, or to churn the sediment in the course of doing so. 2 things follow, and between them they account for everything the place is famous for. The first is that whatever sank stayed exactly as it landed. A fish dying near the surface drifted down and settled into the mud entire, and nothing came for it. Green river fish are preserved with their fins spread and their scales in position, and their last meal still sitting inside them. More than 20 kinds of fish, over 100 kinds of insect, plants, birds, crocodilians, turtles, and now and then an animal that had been living in the trees along the shore and ended up in the water. The second is the layering. With nothing burrowing through it, sediment accumulated on that floor in undisturbed sheets, and it did so on a seasonal rhythm. Through the warm part of the year, the lake bloomed and laid down a pale carbonate layer. Through the cooler, drier part, a darker layer of finer material settled over it. Light, then dark. Light, then dark. 1 pair for every year the lake existed. Paired layers of that kind are called varves. These are fractions of a millimeter thick, and they are all still there. A piece of green river shale small enough to hold in one hand contains more years than the person holding it is going to be given. So the lake kept a calendar, not an estimate, not an average rate of accumulation to be worked backward from, but an actual count, year on year, with none of them missing, running continuously for a very long time, 52 million years ago. Which means a fossil out of that shale can in principle be placed within a particular year. Not a period and not an interval of a few thousand, but a single turn of the seasons in the early Eocene, identifiable because the lake wrote it down as it happened. In 2003, out of those beds came a bat. Nancy Simmons and colleagues described it in Nature on the 14th of February 2008, and the skeleton is close to complete. The animal is about 52.5 million years old. Its wingspan runs to roughly 30 centimeters, a body you could close your hand around with wings a little wider than a paperback, and it weighed about what a small apple weighs. It is a bat by every test that matters. The wing is a proper bat's wing, built from hugely elongated fingers with skin stretched between them, and the animal flew under its own power. But it carries claws on all 5 fingers. Modern bats have kept a claw on the thumb and occasionally on one other digit. This one had the full set, which points to an animal still doing a great deal of climbing. Its legs are long. Its wings are short and broad. Taken together, the proportions suggest a fluttering, undulating sort of flight, possibly alternating with glides, rather than the fast level cruise of a modern insect hunter. Its name means clawed bat, and that is the useful thing to call it. Now the ears, and it is worth being precise about what echolocation is, because the word gets thrown around loosely. Sitting in a dark room, you can hear a great deal. Someone breathing, a clock, a car passing outside. All of that is passive. Sound is arriving, and you are locating its sources. What you cannot do is hear the walls, the shape of the room, the position of the furniture, the doorway you would have to find to leave. None of that is available, because none of it is making any noise. A bat in that same room hears the walls. It produces a call, usually very loud and usually above the range we can register, and reads the returns, and from their timing and shape assembles a spatial picture that it refreshes many times a second while flying in the dark in pursuit of something that is also flying. Most bats generate those calls in the larynx. In an echolocating bat, the cochlea, the spiral of the inner ear where sound gets converted into nerve signal, is markedly enlarged relative to the size of the skull. Handling that volume of high-frequency information requires hardware, and the hardware shows up in the bone. The clawed bat's cochlea is small. It falls within the range of ordinary mammals that do not echolocate at all. That was the 2008 reading, an animal that could fly and could not echolocate. Flight arriving first, the hearing following afterward. It answers a question that had been open for decades, and it carries an appealing logic with it. A climbing animal takes to gliding. Gliding becomes flapping, and only later, once the creature is already airborne and working at night, does the sonar arrive to make the work efficient. 2 years afterward, a different group examined the same specimen and looked at a different bone. In bats that echolocate with the larynx, there is a physical connection inside the skull between the small chain of bones supporting the voice box and the bone of the ear itself. The two articulate, they touch. The reason is straightforward once it is said out loud. An animal producing calls loud enough to be useful needs its ear to know precisely when it is shouting, both to protect itself from its own volume and to time what comes back against what went out. A hard link between throat and ear supplies that. The 2010 paper argued that this connection is the more reliable indicator, better than cochlea size, and it reported that the connection appears to be present in the clawed bat, which reopened the whole thing. Both readings were made carefully by people who know the material on the same skeleton. The small cochlea is not in dispute. Whether a small cochlea rules out echolocation altogether or only rules out the elaborate high-performance version that modern bats run is a separate question, and an early, crude, low-frequency system, enough to register that something solid is ahead but not enough to pick an insect out of a cluttered background, might not require much cochlea at all. It has not closed. Work continues around the edges of it from other directions. A study in 2024 looked at whether the properties of the early Eocene atmosphere itself eased the passage from gliding into powered flight. What would help most is more specimens, and more specimens are difficult, because a complete articulated bat is a rare object even in a lake that keeps everything. That is worth sitting with for a moment. Most of the past is shut to us by plain absence. The animal was never buried, or the rock was never lifted, or the layer wore away before anyone thought to look. Here there is very nearly everything, a whole skeleton, out of a lake that kept its own calendar, resolvable in principle to 1 year 52 million years back. And the question stands open anyway, not because the evidence is thin, but because the evidence is honestly ambiguous, which is a rarer place to be standing than certainty, and a more interesting one. Another lake was doing the same work a few million years later, and in some respects doing it better. It sat in a volcanic basin in what is now Germany, and what has come out of it exceeds Green River in nearly every category: soft tissue, stomach contents, the outline of fur, the colour still sitting in the wing cases of beetles. It is among the richest fossil deposits anywhere on Earth. And every slab lifted out of that pit begins destroying itself within hours of reaching the air. Oil shale from Messel is roughly 40% water. That single property governs everything about how the place is worked. Lift a slab out of the pit, set it down in the sun, and within a few hours the water starts leaving. The rock shrinks as it goes. It cracks along the bedding first, then across it. then into flakes, and then into something closer to ash than to stone. Whatever was inside comes apart along with it, and messel slabs very often have something inside. An afternoon of dry air will undo a fossil that has held together for 47 million years. So the work runs against a clock. Picture sitting on the floor of that pit with a slab across your knees, watching the surface of it change color as it dries, knowing there is a fish or a beetle or the edge of a wing somewhere beneath your hands that you cannot see yet and may not get to. What was eventually worked out is not conservation in any ordinary sense. It is a transfer. The slab is kept wet from the moment it comes up. The fossil is then exposed from one side, slowly, underwater or under a fine spray, until bone or outline begins to show. Resin is poured over that exposed face, epoxy or polyester, and left to cure into a solid plate. Then the whole thing is turned over and the remaining shale is taken off the back, all of it, until none of the original rock is left anywhere. What remains is the fossil, lying on a sheet of plastic in precisely the arrangement it held in the ground. The stone that carried it for 47 million years is discarded, because the stone is the thing that was going to destroy it. That method did not come out of a university laboratory. It was worked out in the early 1970s by amateurs, local collectors, weekend fossil hunters, during the narrow window after commercial mining stopped in 1971 and before the state began preparing the site for its next purpose. The next purpose was rubbish. Messel had been quarried for its shale since 1859, and when the economics finally gave out, what remained was a hole that happened to be large, deep, and conveniently close to Frankfurt. In 1974, the work of turning it into a landfill began. What followed was a long, unglamorous local argument that ran for the better part of 2 decades, with residents and collectors and scientists on one side and a waste disposal plan on the other. It was won slowly and by attrition. The state of Hesse bought the site outright in 1991, which settled it, and on the 9th of December 1995 the pit was inscribed as a World Heritage Site. 17 years of petitions and committee rooms stand between the fossils of Messel and a hole full of household refuse. The pit is volcanic in origin. Around 47 million years ago, rising magma met groundwater beneath what is now central Germany, and the steam explosion that followed blew a roughly circular crater into the ground. It filled with water. Being deep for its width and sheltered from the wind, that water never turned over, and the bottom of it went still and airless. The same arrangement as the lake in Wyoming, arrived at by an entirely different route. The preservation that resulted is hard to convey in general terms, so it is better done through particulars. The beetles have their colors, not pigment. Pigment does not survive. Beetle iridescence is structural, microscopically thin layers built into the shell, spaced so that light reflecting off the top of one layer interferes with light reflecting off the layer below it, reinforcing some wavelengths and cancelling others. It is the same physics as an oil film on a wet road. And because the effect is a physical arrangement rather than a chemical one, it can survive being pressed flat in mud for 47 million years. The layers are still in place. They are still doing it. The shade has almost certainly shifted, since compression alters the spacing and altered spacing changes, which wavelengths come back, so the green is probably not the exact green it once was. But an insect that died in the Middle Eocene is lying in a drawer in Frankfurt, and it is still shining. There are animals with their final meal identifiable inside them. Not a stain where the gut used to be, but the contents themselves. Leaves, seeds, insect fragments, sometimes specific enough to name the plant. There are bats with the remains of what they had been eating still in place. There are birds with feather outlines, mammals with the shadow of their fur, and the fine membrane of a wing rendered as a dark film on a pale plate. The most famous thing ever taken out of that pit is also the one that caused the most trouble, and the trouble had nothing whatever to do with the fossil. On the 19th of May 2009, at the American Museum of Natural History in New York, a small primate skeleton from Messel was presented to the press. It is about 47 million years old and very nearly complete, among the most complete primate fossils ever recovered anywhere, with the outline of the body preserved and the contents of the gut still sitting in position. It was given the name Darwinius massillae and a nickname, Ida. The announcement arrived with a book already written and a television documentary already made, and with the animal described as a missing link in human evolution. The correction took months rather than years. Specialists examined the teeth and the ankle and placed the animal among a group of early primates whose living relatives are lemurs and lorises, a real branch of the family and an interesting one, and not the branch that leads toward monkeys, apes, or anybody listening to this. The paleoanthropologist Christopher Beard put it about as plainly as it can be put. Ida is as far from the human lineage as you can get and still be a primate. What is worth saying is that the fossil was never the problem. The specimen is remarkable and remains so, and nothing found since has made it less valuable. What went wrong was the order of operations, a press conference, a book, and a documentary arriving in front of the scrutiny rather than behind it, and a claim cut to the size of an audience rather than to the size of the evidence. The process itself worked. The claim was tested, found too large, and corrected quickly and in public, which is what the process is for. Corrections travel badly, though. The headline reached a great many more people than the retraction ever did, and a genuinely extraordinary fossil now moves through the world carrying a reputation it did nothing at all to earn. There is something quieter in that pit, and it has never needed a press conference. Messel has produced more than 70 small horses, the European cousins of the animals weathering out of those Wyoming hillsides, about the size of a large dog, several toes to a foot, low rounded teeth for browsing the forest floor. They turn up in every condition and at every age. Some of the mares were pregnant, not inferred to have been pregnant. The foals are there, inside them, in position, curled the way a fetus curls, with the soft tissue that held them preserved alongside. The ligament, the attachment, the working architecture of a mammalian pregnancy in the middle of the Eocene, laid out flat and legible. It has taught us a great deal about how mammal reproduction was already operating 47 million years ago, which is why those specimens matter to the people who work on them. It is also a mare who was carrying a foal on some particular afternoon beside a lake in what is now Germany, and the two of them are exactly as they were. Whatever happened that day happened quickly. And then nothing happened at all, for a very long time. Messel is a lake in a hole. It was perhaps a kilometre across, and it lasted something on the order of 1 million years, and everything in it records one small patch of country in extraordinary detail. While it was filling, something much larger and far less dramatic was going on in the shallow sea that still ran across the middle of the world. Nothing there was being buried whole. Nothing was keeping its colour. Small things were living and dying on a warm seafloor in numbers that resist being written down, and settling and accumulating for tens of millions of years without interruption into a layer that would eventually be lifted out of the water and cut into blocks. On the floor of that sea, in water shallow enough for sunlight to reach the bottom, something was sitting still and slowly getting larger. It was flat and round, shaped like a lens or a coin, and it was not going anywhere in particular. Fine threads extended out of it through pores in its shell, spreading across the sediment, catching particles, drawing them back in. It had been doing this for some time. It would go on doing it until it died, at which point it would settle a few millimeters into the ooze and remain there. It was one cell, not a colony of cells, not a simple animal, not a small shelled creature of the sort that turns up in a rock pool. One cell, a single continuous body with one set of internal machinery, which had built itself a house of calcium carbonate divided into a spiral of chambers and had then filled every one of them. That is how they grow. A young one begins with a single small chamber and adds another beside it, then another, each a little larger than the last, coiling outward in a flat spiral. Cut one across and the interior looks like the inside of a nautilus rendered at a fraction of the scale. An ordered sequence of compartments, all connected, all occupied by the same individual. And it was not living in there alone. The large ones, these included, are understood to have carried photosynthetic algae inside their own cell, held out toward the edges where the light could still reach them, converting sunlight into sugars the host then drew on, which is why they needed clear, shallow water and could not survive in the deep, and why they were able to grow the way they did, a single cell in a mineral house running a garden. Their name comes from the Latin for a small coin, which is what they look like weathering out of a rock face. Most of them ran between 1 and 5 centimeters across, already an absurd figure for a single cell. The largest species went considerably further than that. One reached 16 centimeters, roughly the width of a hand with the fingers spread, and the biggest foraminiferan ever measured comes in near 19. A cell in a human body is generally on the order of 1/100th of a millimeter across. These were something like 16,000 times wider. There is a vocabulary problem in all of this that is worth staying with rather than skating past. Calling the thing an animal is straightforwardly wrong. Foraminifera are not animals, and they are not plants or fungi either, but members of a branch of life that most people have never had occasion to hear named. Calling it a single organism is correct and incomplete, given that a good deal of what it was doing was being done by other organisms living inside it. Calling it small is untenable at 16 centimeters. Calling it simple is hard to defend while looking at the architecture of the shell. So what should we make of a thing like that? Probably that the categories were built for creatures of roughly our own size moving at roughly our own speed, and that they were assembled for convenience rather than for accuracy. The Eocene seafloor was full of things that do not sit comfortably in them. This one merely happens to be large enough that the poor fit is visible to the naked eye. That same sea was keeping two entirely different kinds of record at once. In one place it was manufacturing rock, anonymous, quantitative, made of organisms that nobody would ever name one at a time. At its northern margin, in what is now northern Italy, it was doing something close to the opposite. The site is Monte Bolca, and the best known part of it is a quarry called the Peschiara, the fish bowl, which has been producing individual fossil fish of extraordinary quality since the middle of the 16th century. They come out complete, fins spread, scales in position, body outline intact, and in some specimens with traces of the original patterning still readable across the flank. The rock is a fine limestone from a shallow lagoon of about 50 million years ago, and what it holds is not some unrecognizable alien assemblage. A great many of the fish families on that reef are families still living on reefs today. Bolca sits close to the first point in the whole record where a modern-looking shallow water fish community turns up. The human history of the place runs nearly as long as anything in this account. The first documented mention of a Bolca fossil dates to 1550, describing material held by the Holy Roman Empire's ambassador to Venice. The first published illustration appears in 1622 in a catalogue of an apothecary's collection in Verona. Through the 18th century, a series of Veronese noblemen assembled large private holdings, and by the end of 1791, one of them, a collection belonging to Giovanni Battista Gazzola, contained over 1,000 well-preserved fossil fishes. They were argued about fiercely, not about which species they were, which nobody at the time could have settled, but about what a fossil is at all, whether these objects had ever been alive, and how a fish comes to be lying inside a mountain. Charles Lyell gave this epoch its name in 1833. People had been prying these fish out of that hillside, drawing them, cataloguing them and disagreeing about them for the better part of 300 years before there was a word for the stretch of time they came from. At the southern edge of the same sea, the anonymous record went on accumulating. Across the shelf that covered what is now northern Egypt, shells settled onto the floor in quantities that make the word many useless, and kept settling for millions of years with very little mud or sand coming off the land to dilute them. What that produced is a limestone composed almost entirely of organisms, the Mokattam beds, and one of its abundant species carries the name Nummulites gizehensis, after the plateau it helped to build. There is a property of that rock which decided the shape of everything later made from it. Sediment laid down on a quiet sea floor accumulates in horizontal sheets, and limestone formed that way splits cleanly along them. As the beds were later lifted and stressed, vertical fractures developed through the stone at reasonably regular spacing, horizontal partings, vertical joints. So the rock arrives at the quarry face already close to rectangular. A mason with copper tools and wooden wedges is not carving a block out of a shapeless mass. He is persuading the stone to come apart along surfaces it was already inclined to come apart along. The geometry of the quarry was set by the geometry of the sediment, and the geometry of the sediment was set by the way small things settle through still water. Those blocks are that size and that shape because of how a warm sea puts itself to bed. The quarries in those hills have been worked more or less continuously ever since, and a great deal of Cairo is built out of them. So it is not only the monuments. Lay a hand flat against the wall of an ordinary building in that city, something modern, something with people living in it, and there is a fair chance you are touching a Middle Eocene sea floor, compressed and lifted and cut square, still packed with the flat coiled shells of single cells that spent their lives sitting in the light, farming algae in water that has been gone for 40 million years. That sea ran east to west through the warm middle of the world, and everything about it was ordinary, salt, sunlit, shallow along its edges, quietly manufacturing stone. Far to the north, there was another body of water behaving nothing like it. The Arctic Ocean of the Middle Eocene was very nearly enclosed, a basin with only narrow and shallow connections to anywhere else, and rivers were emptying into it from every direction, off a continent that was warm and wet and covered in forest. Water that fresh does not sink and mix, it floats. The top of that ocean had almost no salt in it. Rivers were arriving from every direction, off a continent that was warm and wet and covered in forest and shedding rainfall at rates no Arctic drainage manages now. What they delivered was fresh water, lighter than seawater, and it stayed where it was put. In an open ocean, a lens like that gets broken up and stirred away within a season. This basin was very nearly closed. Its connections to anywhere else were narrow and shallow. The water beneath was layered and still and did not turn over, and nothing arrived from outside with the energy to mix it. So the fresh water sat on top, not for a season and not for a century, for something on the order of 1,000,000 years, and something moved in. A zolla is a small floating fern, and it is still alive. It grows on ponds and ditches and slow water across much of the world, and if you have ever looked at a pond surface covered in a fine green scurf and assumed it was algae, there is a reasonable chance you were looking at this instead. An individual plant is 1 centimeter or 2 across, overlapping scale-like leaves, a few fine roots trailing underneath, the whole thing light enough to lift on a fingertip. You could hold several hundred in a cupped hand without difficulty. It has one trick, and the trick is why any of this happened. Inside cavities in its leaves, Azolla houses a cyanobacterium, a single-celled organism, one of the oldest lineages on Earth, which takes nitrogen straight out of the air and converts it into a form the plant can use. Nitrogen is normally the limiting nutrient in fresh water. It is the reason ponds do not simply fill with vegetation and stay filled. This fern does not have that constraint. It manufactures its own supply, and given light and warmth and still water, it can double its mass in a matter of days. People have been exploiting that for a very long time. Azolla is still grown deliberately in rice paddies across parts of Asia, floated on the flooded fields as a living fertilizer. Because a plant that makes nitrogen out of thin air and then rots into the mud is an extremely useful thing to have. Put that plant on a body of fresh water the size of the Arctic Ocean, in a climate with no frost in it, and the arithmetic runs away. Between roughly 49 and 48 million years ago, that basin carried fern. Not a bloom in the sense of a summer algal event on a lake, a condition sustained across hundreds of thousands of years, with the plants growing, reproducing, dying and sinking through the fresh layer into the airless water below, where nothing was waiting to decompose them. They accumulated on the floor of the Arctic Ocean for about 800,000 years. That is the part that resists being held properly. A plant you could balance on a finger, covering a polar ocean basin continuously, for a span 8 times longer than our own species has existed, laying itself down on the bottom a fraction of a millimeter at a time, in the dark, under a lid of river water, while the forests along every shore of that basin went on shedding leaves into it. Knowing any of this at all required going and getting it was not straightforward. The Central Arctic Ocean had never been deep-cored. In the summer of 2004, an international drilling expedition went after the Lomonosov Ridge, a submarine mountain range running across the basin at around 87 degrees north, and the arrangement they used to do it is worth picturing. The drilling vessel was an ice-strengthened ship called the Vidar Viking, modified for the job with a hole cut clean through her hull, a moon pool, and a drilling rig capable of hanging more than 2,000 meters of pipe down through the water and into the sediment beneath. To take a core, she had to hold position within a few meters for hours in moving pack ice. She could not have done it alone. 2 other icebreakers, one Swedish and one a Russian nuclear vessel, worked upstream of her in the drifting flows, cutting the ice into pieces small enough that what reached the drill ship would part around her instead of pushing her off station. 2 ships breaking ice so that a third one could stay still. They brought up over 400 meters of sediment, and in the middle Eocene section of it, the fern is unmistakable. Layer after fine layer of it, and crucially, with the reproductive structures included. Those are fragile. They do not survive being carried any distance down a river system. Their presence in the sediment says the plants were living and reproducing in that basin rather than being delivered to it from somewhere else. Which brings up the argument, and the argument deserves to be laid out honestly, because this is a case where a beautiful idea has run somewhat ahead of the evidence. The idea is carbon. A plant growing takes carbon dioxide out of the air. A plant dying in oxygen-free water does not rot and does not give that carbon back. It gets buried, and the carbon leaves circulation. Do that across an entire ocean basin for 800,000 years, and the quantity involved becomes, in principle, large enough to matter to the whole planet. And the timing is striking. The fern interval sits at almost exactly the point where the long Eocene warmth stops holding, and the world begins its slow descent toward ice. It is a genuinely elegant proposal. A fern the size of a fingernail quietly taking the heat out of the earth. What the record actually supports is narrower than that. That the plant was there, growing and reproducing in enormous quantity over a very long interval is well established. That it removed carbon is straightforward chemistry. Whether it removed enough carbon to have driven global cooling is not established, and the estimates involved carry wide margins in every direction. How much of the basin was covered at any moment? How much of what grew was actually buried rather than recycled? How much of the sediment reached the deep basin at all? Some work from the last 15 years has questioned the picture of continuous basin-wide blooms altogether, arguing instead for episodic delivery from the margins of the basin rather than sustained growth across the middle of it. And there is a rival explanation for the cooling that does not need the Fern in any capacity. India had been driving north into Asia for millions of years, and around 50 million years ago the ground between them began to rise. When silicate rock is exposed to rain, the chemical reaction that breaks it down consumes carbon dioxide out of the atmosphere and eventually locks it away as carbonate on the sea floor. Raising a mountain range exposes a colossal quantity of fresh rock to weather and turns a slow global process up. That mechanism is well understood. It operates on exactly the right timescale, and its start date sits uncomfortably close to the ferns. So the honest position is this: we know a fern covered a polar ocean for the better part of 1 million years because it is there in the mud, in layers, with its spores in place. We do not know what that did to the planet. The coincidence in timing is what suggested the hypothesis in the first place, and coincidence in timing is a reason to look carefully rather than a reason to conclude anything. It may turn out to have been the mountains. It may turn out to have been both, working together, with neither sufficient on its own. It may turn out that a great deal of carbon went into that basin, and it still barely moved the global figure. What is not in doubt is the fern, and the fern does not require the causal claim to be worth an hour of anyone's attention. An ocean at the top of the world, capped with river water, holding no ice at all, green from shore to shore with a plant small enough to lose in your hand, and staying that way without interruption, while entire lineages of animals came and went on the continents around it. Whatever was responsible, the direction of the world did change around this point. The warmth stops holding. The carbon dioxide begins its long decline. The deep ocean starts to cool, and the descent that ends with permanent ice at the southern end of the Earth gets underway. 8 million years before it arrives. Except that partway down that slope, the whole thing turned around and went back up. For roughly 500,000 years, the Earth warmed again. Not a flicker in the record, not a wobble to be smoothed out, a substantial, sustained reversal, arriving at a moment when every mechanism anyone understands should have been pulling hard in the opposite direction. It has never been satisfactorily explained. 500,000 years has been, for most of this account, close to a rounding error. The warm plateau of the early Eocene ran 8 times longer. The fern accumulated on the floor of the Arctic Ocean for nearly twice as long. Even the carbon event at the very base of the epoch, the one that shrank the horses and opened the roads north, the one that felt like a catastrophe right up until somebody put a clock on it, lasted rather less than that. So a warming occupying 500,000 years ought to be a minor feature. A bump on a long descent, worth a line in a paper and not much more. It is the piece of the Eocene that nobody can account for. Around 40 million years ago, 8 or 9 million years into a cooling that had been running steadily and in one direction, the temperature stopped falling and began to climb. Not briefly. The rise held for something on the order of 500,000 years, reached its maximum right around the 40 million mark, and then let go, and the cooling resumed as though nothing had happened. Standing anywhere on Earth through it, you would have registered nothing whatsoever. Several degrees of warming spread across 500,000 years amounts to a change no instrument of ours would pick up inside a human lifetime. A fraction of a degree per 1,000 years. Invisible against ordinary weather. Invisible across 100 generations of anything alive. The ocean registered it. In the deep sea, where cold water holds more dissolved carbon dioxide and therefore turns more corrosive as the system loads up, the shells on the seafloor began to dissolve. That dissolution horizon is one of the clearest markers of the interval, and it turns up in cores from ocean basins that had nothing to do with one another, which is how we know the thing was global rather than local. To understand why this is a problem rather than merely an event, it is necessary to know how the planet normally handles its own carbon, because the planet has a mechanism for it, and the mechanism is quite good. Carbon dioxide enters the atmosphere from volcanoes, not dramatically, a steady, unglamorous seep from volcanic arcs and mid-ocean ridges, going on continuously for as long as there has been plate tectonics. Carbon dioxide leaves the atmosphere chiefly through rock. Rainwater absorbs a little of it on the way down and arrives at the ground as a weak acid, and that acid slowly attacks the silicate minerals that make up most of the continents. The products of that reaction wash down rivers into the sea, where marine chemistry and marine organisms lock the carbon into carbonate and bury it on the sea floor. It is not fast. It is relentless. And here is the property that matters. The reaction runs faster when it is warmer. Chemical weathering accelerates with temperature, and a warmer world also runs a more vigorous water cycle. More evaporation, more rainfall, more water moving across more rock. So the removal rate is not fixed. It rises and falls with the climate itself, which makes it a thermostat. Add carbon dioxide to the air and the world warms. The warming speeds up weathering. The faster weathering pulls carbon dioxide back out. The world cools again. Take carbon dioxide out and the same loop runs in reverse. A cooler, drier world weathers more slowly. Volcanic carbon accumulates and the temperature comes back up. Left alone, the system corrects itself. It is not instantaneous. The response time of that feedback runs somewhere in the range of 100,000 to a few 100,000 years, which is why the Earth can be knocked sideways for a while before being pulled back. We have already watched it work. The carbon event at the start of the Eocene was a hard shove, an enormous quantity of carbon delivered in a few thousand years, and the system absorbed it, held the new temperature for 70 or 100,000 years, and then spent another 50 to 100,000 putting the carbon back into stone and returning the world to roughly where it started. That whole sequence is the thermostat doing its job at exactly the speed the thermostat is supposed to work. Now set the middle Eocene warming beside it. 500,000 years. That is not inside the thermostat's response time. That is well past it. Whatever pushed the temperature up should have been met, corrected and cancelled somewhere around the 200,000 year mark, and instead the warmth simply stayed for 2 or 3 times as long as the correction should have needed, and then ended for reasons no more obvious than the ones that started it. There is no shortage of proposals and they are all serious. One argues that the thermostat had been worn down. By this point, the planet had spent something like 15 million years in exceptional warmth, with heavy rainfall over most of the land surface and weathering running hard the entire time. Rock that is easy to weather does not last forever under those conditions. The reactive material near the surface gets used up, and what remains is more resistant. On that reading, the continents had become harder to dissolve, the feedback had lost some of its strength, and the ordinary volcanic supply of carbon dioxide was simply able to accumulate for longer than it should have before the sink caught up with it. A second points at the orbit. The shape of Earth's path around the Sun is not fixed. It stretches and relaxes between more circular and more elliptical on several overlapping cycles, one of about 400,000 years, another of roughly 2.5 million. Around this time, those two cycles reached their minima together, producing an unusually long stretch in which the orbit stayed close to circular and the seasonal contrast stayed unusually steady. The carbon isotope record through the interval is genuinely unstable, swinging in ways that suggest a carbon cycle under some kind of sustained external pacing, and the orbital coincidence is the most obvious candidate for what was doing the pacing. A third, published in 2023, concerns clay. Clay minerals form as rock weathers, and their formation is usually filed on the drawdown side of the ledger. But under certain conditions, particularly in the sea, the process can work the other way and act as a source of carbon dioxide rather than a sink. That paper argues a shift in how and where clays were forming was central to holding the warmth in place. None of the three has closed the question. They are not necessarily rivals. Some combination is entirely possible, and the honest state of the field is that the interval is well described and poorly explained. Which is the interesting kind of not knowing. This is not a case of thin evidence. The record is excellent. The event is legible in every ocean basin and in continental sections on land. The timing is tightly constrained. The magnitude is bounded within reasonable limits. What is missing is not data. What is missing is a mechanism, and the mechanism is missing in a way that pushes back against how the whole system is understood to regulate itself. There is a piece of arithmetic worth putting beside that. A geologist who spends an entire working life on this problem, 40 years, from a first field season to a last paper, will have spent that career examining an interval something like 12,000 times longer than the career itself. The person is studying a stretch of the past in which their whole professional existence would occupy the width of a pencil line on the graph. Whatever was holding the warmth up eventually gave out. The temperature turned over and started down again, and this time it did not come back. That 500,000 years around the 40 million mark was the last time the Eocene was warmer at the end of an interval than it had been at the beginning. Everything after it runs one way. The descent resumed and steadied. For the next 4.5 million years, the temperature came down. The carbon dioxide came down alongside it. The deep ocean chilled by degrees, and nothing interrupted any of it. Then, 35.5 million years ago, two objects arrived from outside the Earth within about 25,000 years of one another. And one of them opened a crater 100 kilometers across. Popigai is 100 kilometers across. It lies in northern Siberia, well above the Arctic Circle, in country that is now tundra and permafrost and very nearly empty of people. From the ground it does not read as a crater at all. 100 kilometers is far too wide to register as a shape when you are standing inside it. From orbit, it is unmistakable. A broad, shallow circular basin with a ring of low hills around the rim and a river running across the middle. The object that made it was somewhere between 5 and 8 kilometers wide. There is no useful way to convey the energy involved, because the units stop carrying meaning at that scale. What can be conveyed is what happened to the rock. The ground it struck was crystalline basement, old, hard continental rock with graphite scattered through it. Graphite and diamond are the same element arranged differently, and the pressure required to turn one into the other is enormous and normally available only deep inside the planet. That pressure became available in northern Siberia for a few seconds across a very large area 35.5 million years ago. What resulted is among the largest diamond deposits known anywhere. Not gem material, small dark industrial stones, the sort used for cutting and grinding, but an extraordinary quantity of them, manufactured in an instant out of a mineral that had been sitting quietly in that ground since long before there were animals to walk on it. Within about 25,000 years, a second object came in on the other side of the world. That one hit a shallow sea along the eastern margin of North America in what is now Virginia. It was smaller, 3 to 5 kilometers, and the crater it opened has been buried ever since beneath sediment and beneath the lower part of Chesapeake Bay. It went unrecognized for a long time because there is nothing on the surface to see. What there is instead is a water problem. The shattered rock under that part of Virginia still holds a mass of ancient brine trapped by the impact, and wells drilled into it come up salt. Both events left a mark on the entire planet. A large impact throws molten rock into the upper atmosphere, where it cools into small glassy droplets that then fall back across an enormous area, in some cases most of a hemisphere. Those droplets settle into whatever sediment is accumulating and form a thin, distinctive layer that can be traced worldwide. There are 2 of them in the late Eocene close together, and they are among the most useful time markers anywhere in that part of the record. Which makes the question of what these impacts did unusually answerable. Nobody has to estimate where in the sediment to look. The layer is right there, and everything above it is afterward. Everybody brings the same expectation to this, and it comes from one specific event. 66 million years ago, an object roughly 10 kilometers across struck a shallow sea off what is now the Yucatan Peninsula, and by the time the consequences had finished working through, most of the species then alive were gone, including every dinosaur that was not a bird. It is the best-known event in the history of this planet, and it established a sequence in almost everyone's mind. A large object arrives, the sky darkens, a world ends. That template was strong enough that it became a working hypothesis here as well. For years, there was a serious proposal that the late Eocene impacts had contributed to the cooling, that they had shoved the climate somehow, or set off the transition that was coming, or at minimum, left some detectable disturbance in the system. It has now been tested carefully. In December 2024, Bridget Wade and Natalie Cheng at University College London published a study that did the obvious thing thoroughly. They went to marine sediment cores spanning the interval, located the impact layers, and worked through the foraminifera, the same single-celled shell builders that have been keeping the books through this entire epoch, from the trays in Paris to the pyramid blocks, sampling continuously across the horizon. Over 1,500 specimens at a resolution of roughly 11,000 years, which for an event of this kind is fine-grained. The oxygen locked into those shells records temperature and the amount of ice on the planet. The carbon records what the carbon cycle was doing. If either impact had done anything measurable to either quantity, it would show. Nothing shows. There is no shift in temperature across the layers and no excursion in the carbon. No extinction registers among the plankton, not in the foraminifera, not in the chalk-building organisms alongside them, and nothing on land responds either. Across the 150,000 years following the impacts, the record does precisely what it had been doing before them, which is to cool, slowly, at the rate it had already been cooling for millions of years. There is one shift inside the study's window, and it sits in the wrong place. Something moves in the isotopes about 100,000 years before the collisions, part of the long descent, unconnected to anything arriving from space, and finished well before either object came down. The only signal anywhere near those craters predates them. The reason is probably twofold, and neither half is mysterious. The first is size. Energy scales steeply with the mass of the thing arriving, and an object 10 kilometers across delivers several times what one of 6 or 7 does. These were enormous. That one was in another category altogether. The second is what they landed on, and it may matter more. The impact that closed the Cretaceous struck a shallow marine platform loaded with sulfur-bearing rock, and vaporized a colossal quantity of it straight into the upper atmosphere, where sulfur forms a fine, reflective haze and stays aloft for years. The leading understanding of that extinction is that most of the killing was done by the resulting dimness and cold, a sky that stayed dark long enough for photosynthesis to fail across most of the planet. Poppygays struck hard, crystalline rock in the middle of a continent. The other struck a shelf sea, but a fairly ordinary one. Neither had the chemistry available to put a lid over the sky. A large impact is a local catastrophe of the most complete kind, and a global event only if the ground it lands on cooperates. So the thing to set down, gently, is the template. Most of us learned that sequence early, and it is true, and it is a good story. It also happens to describe one impact out of all the impacts this planet has absorbed. It is not a rule. It is an outcome that required a particular size, a particular angle, and a particular kind of rock underneath, all arriving together on one very bad morning in the Cretaceous. Two of the largest objects to strike the Earth since then came down inside the Eocene, 25,000 years apart. In northern Siberia, everything for a great distance around simply ceased. In Virginia, a seafloor was excavated and thrown across the coastal plain, and the whales went on swimming. The forests at the top of the world went on shedding their needles every autumn and standing bare through the dark. The small coin-shaped cells went on sitting in the light in the shallows of the Tethys, farming their algae, laying down the stone that would eventually be cut into blocks and stacked on a plateau outside Cairo. Nothing that mattered to the planet as a whole was interrupted by either event. The record does not so much as flinch. Whatever ended this epoch then did not arrive from outside it. It had been underway for 8 million years before those craters opened. It was chemical rather than violent. It moved at a speed no animal alive could have noticed, and by the time the sky fell twice, it was already most of the way through. The carbon dioxide had been coming down and down since the Fern, or since the mountains, or since both, or since something not yet identified, and somewhere below a threshold that had not been crossed in a very long time, at the far southern end of the world, the snow that fell in winter began to still be lying there at the end of the summer. For something over 10 million years, it drifted. Handkanina was a single cell that lived in open water, carrying long, hollow spines out from each of its chambers, a structure for staying up in the sunlit part of the ocean and for holding the fine threads of the cell out into it, the way a web is a way of occupying a great deal of space at very little cost. It fed, it divided, it sank when it died, and the shells accumulated on the floor of every ocean it lived above, layer upon layer, for a span longer than the entire history of the great apes. And then, in a roadside quarry above the Adriatic coast of Italy, at one level in a sequence of pale marl, it stops. That level is where we now are. Everything in this account, the carbon at the beginning, the small horses, the crossing through the Arctic, the 4 million year summer, the whales at the waterline, the fern, the warmth that would not leave the two stones, sits below it. What lies above it is everything else, including the room this is being listened to in. The mechanism was carbon dioxide, and it had been falling for a long time. At the height of the early Eocene, it stood somewhere near 1,600 parts per million. Through the middle and late parts of the epoch, it ran between 800 and 1100. Across the boundary, it drops below 600, and somewhere on the way down, it passed through a value that mattered. The modelling puts the threshold in the region of 750, below which snow falling on high ground in the far south stopped melting away entirely each summer. Once that begins, it accelerates itself. Snow and ice reflect sunlight, bare rock and open water absorb it. A patch of ground that keeps its snow through August absorbs less heat than it did the year before, which makes it colder, which helps it keep more snow. The feedback is simple and it is powerful, and it is why the record shows a step rather than a slope. Within a few 100,000 years, there was a continental ice sheet. It is worth being precise about which one, because the shorthand is wrong in two ways. Ice had almost certainly existed on Antarctica before this, in the highlands, in restricted patches, coming and going. What happened around 34 million years ago was the establishment of a large and persistent ice sheet on East Antarctica, the older, higher, larger half of the continent. West Antarctica is a different proposition, lower and largely below sea level, and recent work indicates it remained essentially ice-free even at the peak of the early Oligocene glaciation. The ice did not arrive everywhere, and it did not arrive all at once. It took the high ground first and worked outward from there, and parts of the continent stayed green for a long while afterward. The cause has been argued over for decades, and the argument is worth understanding because the popular version has it almost backwards. The story most people have met runs like this. Australia pulled away from Antarctica. South America pulled away from Antarctica, and the gaps that opened, the Tasman Gateway and the Drake Passage, allowed a current to begin circling the continent without interruption. That current cut Antarctica off from warm water arriving from the north, isolated it thermally, and froze it. It is a satisfying story, and the geography is correct. The causation does not hold up as well as it used to. The difficulty is timing. Reconstructions of when the circumpolar current actually became established vary considerably, and several put its onset a few million years after the ice sheet appeared, which would make it a consequence rather than a cause. The carbon dioxide decline, meanwhile, was underway for millions of years beforehand and passes its threshold at very nearly the right moment. What the field has largely settled on is a division of labor. The long fall in carbon dioxide is what made glaciation possible. That is the driver. The opening of the gateways and the reorganization of southern ocean circulation shaped when and how it happened once it became possible, setting the threshold rather than pushing the world across it. Both were operating. Neither did it alone. On land in Europe, something else was happening at almost the same moment. It was named in 1910 by the Swiss paleontologist Hans Staelin, who called it the Grande Coupure, the Great Break, and the name has stuck because nothing better has been needed. Around 33.5 million years ago, the mammal fauna of Europe changes almost completely. Something like 3/4 of the species present disappear from the record, and a wave of animals arrives from Asia to take the ground. Rodents of the lineages that would produce hamsters and voles and beavers, early rhinoceroses, a range of hoofed animals with no European ancestry at all. The most likely doorway is one we have already stood in. The Turgai Strait, the long, shallow seaway that had separated Europe from Asia, and that the first primates had to get across on their way west during the heat at the beginning of the epoch, was closing as sea levels fell. 22 million years earlier, it had been a barrier that a warming world made passable. Now it dried, and the traffic came the other way, into a Europe that was cooling and drying and had room in it. Whether the turnover was driven by the climate, or by the newcomers, or by both together, has never been fully settled, which leaves the largest question, and it is not about the ending at all. We can say when the ice arrived and roughly why. We can chart the carbon dioxide down through the epoch and match it against the temperature. We can name the animals, date the layers, count the varves, and locate the exact hillside where the whole thing begins. What we still cannot explain is how the world we have just spent this hour inside kept its winters mild. The models reproduce the warmth. They reproduce the shallow difference between the equator and the poles. What they cannot yet reproduce is high-latitude land that stayed above freezing through 4 months of darkness, and the fossils are having the same argument with themselves. The palms saying one thing about Arctic winter temperatures, the teeth of the animals saying something several degrees colder, both measured carefully, neither yielding. It is the same question from two directions, and it is still open. Whatever the answer turns out to be, it is a property of a kind of world this planet has not been in for 34 million years, and it is not going to be settled by anyone in a hurry. Step far enough back, and the Eocene stops looking like an interlude. Sorted across the whole of the last 66 million years, the Earth's climate falls into a handful of settings, and this epoch holds the hottest of them, and then walks down through the next. What came afterward has continued in that direction. The Oligocene is cooler, the Miocene is cooler still and drier, and grass finally spreads across the middle of the continents and rebuilds half the mammals on Earth in the process. Then ice reaches the northern hemisphere as well, and the world begins the long series of advances and retreats we are still inside. Widen further past the Cenozoic and into the whole span of complex animal life, and the ice starts to look stranger than the warmth. Across the last 500 million years, permanent polar ice has been the exception. There have been perhaps 3 intervals like ours, separated by very long stretches in which the poles carried no ice at all and the forests ran to the ends of the Earth. The East Antarctic ice sheet has now been in place for about 34 million years, through every glacial cycle and every warm interval since, never entirely going away. It is the oldest ice on this planet by a very wide margin. It has been there longer than grasses have covered open ground, longer than the Himalaya have stood at anything like their present height, and roughly 12 times longer than our own genus has existed anywhere. And it is a guest. It arrived at a particular moment, for reasons that can be written down, onto a continent that had been carrying forest. Something becomes possible for a creature that lives about 80 years and can nonetheless hold 22 million of them in mind at once. None of the animals in this account could do it. The small horse changing size across 130,000 years experienced no change whatsoever. The whales moving into the water over 8 million years were simply animals at a waterline on a series of ordinary afternoons. The alligators in the polar dark were not enduring anything. They were living in the only world on offer, which is what everything alive has always done. We are doing that tonight as well. This arrangement, ice at both ends, grass across the middle, winters that bite, a sky with this particular amount of carbon in it, is not a baseline. It is a configuration, one of a great many this planet has held, and from inside it reads simply as the world, exactly as the Eocene read, as the world to everything that lived in it. What is unusual about us is not that we stand outside any of this. We do not. We are made of a moment in precisely the way that everything else has been. What is unusual is that we can lie in a warm room in the cold chapter and put a vanished planet back together out of shells and leaf shapes and the chemistry of old mud, and hold it there, whole, a world nobody ever saw, which ended long before there was anything here that could have missed it. That capacity is very recent. It appears nowhere else in the record. So there is a shallow sea over Egypt, quietly making stone out of small coiled cells that spent their whole lives sitting in the light. There is a forest at the top of the world, standing bare in the dark, waiting for February. Somewhere on an Arctic island lies wood that is still wood, 45 million years on, light enough to lift with one hand. A whale 16 meters long is carrying a leg the length of a thumb, and will carry it the whole of its life without once putting weight on it. An ocean is covered over, shore to shore, with a plant small enough to lose in a palm. Beside a lake in Germany there is a mare, and the foal she was carrying, exactly as the two of them were on the afternoon it stopped. On a hillside in Wyoming the teeth get smaller as you climb, and then larger again. At a table in Paris, two men are working through a tray of shells, giving a name to a stretch of time they had no means whatever of measuring. And at one level, in a quarry in Italy, a small drifting thing with spines stops appearing, and everything above that line is ours. None of it is going anywhere. It has already happened, every part of it, and it finished a very long time ago, and it will be sitting in exactly the same place in the morning. The ice came, and it stayed. It is out there tonight, holding the shape it took at the end of that epoch, in the dark, at the bottom of the world. It has held that shape through every winter since, and every summer since, through the entire long stretch it took for anything to appear on this planet that could go and look at it. It was here before the grass. It was here a very long time before us. And it is not waiting for anybody. Neither is the sea it replaced. Neither are the forests that ran to the poles, or the warm, shallow water, or the small, unhurried animals moving through the shade of a world that was perfectly ordinary at the time and is unimaginable now. All of that is finished, and none of it needs anything from you tonight. There is nothing there to hold. Let the day go. Good night.